you might be getting pretty bogged down with the old hydrogen molecule. And you're thinking, why do we keep going through it with all these different angles of things? Why do we talked about orbitals, and we talked about Born-Oppenheimer approximation. We talked about different ways to look at the space. We came up with this idea of Fock space based on wedge products. And now we're going to do something even different. But what I want you to notice is that each time we come up with a new tool, it compacts the notation down. And when we look at really complicated molecules, which is our goal, we don't want to just stay on hydrogen all the time. We want to get up to these iron sulfur clusters and different things like that. So in order to do that, we want to use the most compact structure. So we're going to keep using hydrogen over and over again as the molecule of choice because it's very simple. Now, what I should emphasize is that this hydrogen that we're looking at is a minimal basis model. And a minimal basis model just is one way of looking at the hydrogen molecule. It's not the perfect one or the exact one. The exact one would involve infinite number of dimensions and the ways the electrons could operate and do things like that. So as we go forward, look at this as another tool set. And if it's not getting simpler to look at, then we're doing something wrong. For H2 minimal orbital basis, we have the two symmetric and the two antisymmetric, the two bonding and the two anti-bonding. Should be familiar with this. The simplest ground state is when we just have the bonding orbitals go along there and the centers of the hydrogen molecule are close together. Here's the way to represent that with this little vector notation. Now this isn't the same state function that we're used to before, but this is a specially encoded orbital structure that defines the Hilbert space or Fock space that this does by using these things called creation operators and annihilation operators. And these will use the wedge product to form these. So when we're looking at this, we're really looking at orbitals linked together with wedge products. So here's the different possibilities. The 6 different possibilities for putting 2 electrons in 4 orbitals. These are the most common ones. These are not so common, but they are something to be considered. Now, a short little hurdle here to get over these things called annihilation and creation operators. When we say that something spans a certain distance, then we're indicating that these are the number of dimensions. Minimal basis H2 molecule has 4 different orbitals. No big surprise. And I'm going to label these as I, J, K, L. So it's got 4 dimensions, and this describes the orbitals that those 4 dimensions occupy. So when we do this span, that gives us all the information we need to do this thing called creation and annihilation. We start with something really strange looking. It's just this single cat here with a 0 in there. That's a special one because that says this is the vacuum before you start anything at all. Now, if I had put 4 zeros here, that really would be the same thing as this. But since this is a general thing, this doesn't really describe any particular scenario, so we just always say start with the vacuum. And if we want to begin this, I'm going to start with the annihilation operator. Now, why do I do that? Why annihilation? Because I'm not going to get rid of anything here, but it's labeled as an A. So the A is for annihilation, and it happens that the adjoint of annihilation is creation. Kind of like the opposite of annihilation is creation. Annihilation says remove an electron from orbital I. Creation says add an electron to orbital I. If I try to remove an electron that ain't there, then that returns a 0. So you never want to try to annihilate something that's not there, or the whole expression just collapses to 0. Now it's interesting to note that the value of this vacuum is a scalar, and its value is actually 1. So that's another weird thing, is 0 ket equal to 1? Huh? And this is 0 only because, notice it's not a 0 ket or anything on this side. It means that the value is 0 because you can't do that. It'd be like trying to add an electron to an orbital where there's already one there. So same kind of thing occurs. Now let's build this thing up. Let's build our most common scenario for the minimal basis H2 molecule, and that is these symmetric orbitals filled with 2 electrons, an up and a down. Here's where I add the I, which is the up. So there we go. There's the 1 there, which is the same as orbital G sub up. And here's I and J, and boom, boom, you just put it in there. And the thing is that these describe a wedge product relationship. So every time you do a creation with one of these monsters, then you're using a wedge product to create all this stuff. So all the anti-symmetry required by the Pauli laws and so on are all built into that to net this nice, cute notation. Now, where are we headed? We're headed for quantum computation and quantum computers. Ooh, there's binary. Quantum and binary and computers work very well together. So that's going to be a great thing to look forward to. Take a look at this monster. This is the Hamiltonian. You're going to say, what? You consider that the Hamiltonian? Here's what's called the first quantized Hamiltonian, which you should recognize. Has the Laplacian operators and has the attraction terms for each of the 2 electrons on the 2 protons A and B, and then it's got the repulsion terms between the 2 electrons. So that one should be familiar to you. If not, you need to back up and go through some more of those videos. But here's the Hamiltonian for the second quantization, which uses these monsters, the creation annihilation operators. This just requires a whole nother video. There's a lot behind this, so let's just set the stage for the next video and live with it.